Okay, good morning, everyone. Welcome to our webinar. Today, we're going to be talking about standard versus high resolution spectra for mineral identification. So today we're going to be discussing, it's a relatively short webinar, and we're going to be discussing how standard versus high resolution spectra is used across industry and why it's important. So I guess we'll just get started. So first thing I'll do is introduce Spectral Evolution. We're the leading manufacturer in high quality UV-VIS-NIR spectrometers and spectroradiometers. I am the application specialist here at Spectral Evolution. We were established in 2004, so it's about 21 years we've been in operation, and we're located in Haverhill, Massachusetts, so just outside the Boston area. Now, our primary applications are in hyperspectral applications, remote sensing and vegetation, mining and geology, as well as photonics and calibration transfer. And today we'll be primarily discussing mining and geology applications for high resolution. So I'll start by explaining what a spectrometer is and how a spectrometer works. Spectroscopy is the study of the electromagnetic spectrum as it is emitted or reflected by different materials. The electromagnetic spectrum represents all forms of electromagnetic radiation, which are defined by their wavelengths. So in geology, it's primarily using reflectance spectroscopy, where we measure the radiation reflected by a material. These reflectance measurements are directly linked to the material's chemical structure and bonding. And our spectrometers typically cover the full range from 350 to 2500 nanometers, which is critical for most applications in soil, vegetation, and mineral analysis. With proper radiometric calibration, a spectrometer can become a spectroradiometer and can accurately measure energy across the range, allowing us to identify materials based on their unique spectral signatures and measure energy actually coming down and hitting an object as well. So to outline today's webinar, like I said, what is a spectrometer? I'm going to introduce some of Spectral Evolution's products, and then go over an overview of minerals of interest and resolution for different mining applications or geology applications. And then I'll summarize it and open it up to questions. So Spectral Evolution has 3 different spectrometers that we offer, all differentiated by their spectral resolution. So the standard resolution instrument would be the oreXpress. We've had this for quite some time on the market. And here you can see it's 2.8 nanometer resolution from 350 to 1000 nanometers, 8 nanometer resolution at 1500, and 6 at 2100. So for many different mineral applications, that will suffice for identification, but it does open the door to some ambiguities between some minerals that are very similar. The oreXplorer is our workhorse, high spectral resolution, so 2.7 nanometers in the visible, 5.5 in SWIR 1, and 5.8 in SWIR 2. So that gives you a more refined look at the mineral identification. And then for really explicit and high resolution analysis, we have the oreXpert, which is the highest resolution field instrument on the market today, with 1.5 nanometers in the visible, 3 nanometers in SWIR 1, and 3.8 in SWIR 2. So all of our instruments are designed to be used in the field. They can also be used in the lab, but our goal is to bring lab quality data into the field with the geologists to do mineral analysis actively while they're out in the field. So they can make assessments based on the minerals that they're seeing for vectoring in real time out in the field, and make sure that they are having lab quality data collected in real time as well. So it's also designed to be used in the core shack as well. So it can be battery operated or plugged into any normal wall outlet or generator outlet. These instruments are really versatile and they have no moving parts, so they are very rugged in the field with some bumpers on it to add some a rugged aspect to them. So they're very durable for field use, and they can acquire rapid spectra across a core sample and identify those minerals very readily with the data. So we have a few different accessories that are very common for mineral identification. So one would be the benchtop probe. This allows you to measure powdered samples. So if you have loose material, sediment, and you want to collect spectra off of them and have consistent data, we have these pucks with sapphire lenses. This is not meant to be in the field. This is more of a lab accessory, but internal to this light source is a tungsten halogen light source that shines up, so you can place a rock or place one of these trays on top of the benchtop probe and get good spectra with high energy through that sapphire lens. And like I said, it's sapphire, so it's scratch resistant, and you shouldn't have to worry about rocks scratching it, because it could be harder than most rocks. It's the same window that we use in our contact probe. So this is good for a lot of different applications: sediments, pharmaceuticals, drug industries, and soil applications. We also have two different versions of our contact probe. So we have a 10 millimeter, which is on the top left, and then a 3 millimeter spot size mini probe on the top right. And that little clip on the bottom of the top right, that's a white plate for taking reference measurements. So it's very convenient to just clip it onto the bottom. Now, these two contact probes are, so the regular contact probe would be used for identifying minerals directly in contact with the outcrop. So you'll get a 10 millimeter circle for rocks that have really fine grains. If you're trying to target a specific grain, then 3 millimeters may work better for your mineral identification. All of your spot sizes are going to be a perfect average of that spot size due to our optical design. So just keep that in mind, that 10 millimeter circle is going to be an average of everything in that circle. So if you have several different minerals, you're going to get an average spectra of all of those minerals combined. So 3 millimeters may be more targeted for your application, depending on the setting and what you're trying to target. We also have lenses for standoff measurements. So you can, our bare fiber has a 25-degree cone field of view, and you can manipulate that with different lenses for standoff measurements. So standoff measurement would be if you're using, say, the sun or a light source in the lab where you're taking an area measurement. So you're creating that circle, but in a wider area. So in the field, you would take a reference measurement on a white plate and then take target measurements off of outcrops from waist level or with a pistol grip. That's something that's very effective for characterizing outcrops, ground truthing of remote sensing data as well, and for mineral identification. We have a lot of different averaging tools too to characterize outcrops in real time to speed up acquisition of data. Then we also have this EasyID software that will operate on our field tablet. So we have a ruggedized field tablet that integrates our software, and you can operate your instrument with it. This will run our EasyID software, which allows you to match spectra in real time to spectral libraries. You can also create your own mineral libraries based on your instruments data as well. All of our software is run on Windows, so you can run them on any Windows computer or on our rugged field tablet for field use. So we have 3 different versions of our mineral libraries. We have the USGS library, which includes the JPL library, so that's 466 samples of spectra and 266 minerals. We have 2 optional, so that comes with EasyID. We have 2 optional libraries to extend that with the SpecMIN library with 2,310 spectra for over 794 minerals, and then the optional GeoSPEC high resolution library, which was developed with our oreXpert with 2,310 spectra for 794 minerals. So it's important to understand that a mineral library is limited by the instruments used or the resolutions used to build that library. So if you have a lot of generalizations with coarse resolution spectra in your library, that may interfere with analysis with high resolution. Typically, it will just not match as well and not be relevant, but in certain times it can come up, especially if you're using small match regions. So it's important to understand your library that you're working with when you're doing analysis. So in industry, there's a need for high-resolution mineral libraries. As technology has advanced, we've incorporated a lot of high resolution into libraries, but there's a lot of libraries out there that are using old technology and old specs to create these libraries. So we have created the GeoSPEC high resolution library using Colorado School of Mines Mineral Museum. They're all their mineral samples. And like I said, we got 794 minerals with different alteration types out of this library scanned with our oreXpert. So now I'm going to talk about a couple different applications and how it relates to standard versus high resolution. So first I'll talk about soil and mineral analysis. You can analyze soil fertility, soil contamination, mineral identification, alteration mapping, drill core logging. All of this is affected by the resolution of the instrument that you're using. With any of our resolution instruments, you can be effective in these fields, but it creates some ambiguities between different minerals. So as you can see here on the right, we have a sample of kaolinite. One is using a high resolution instrument and the NaturSpec, and the other is using the ultra high resolution NaturSpec Ultra. And as you can see, that feature is significantly sharper using the higher resolution instrument. Now you can see this with the oreXpress versus the NaturSpec Ultra, or the ultra high resolution expert, sorry, oreXpert. So here you can see halloysite on the left. We see a shift in that feature over to the right, and the features are more defined, whereas they've been broadened by the oreXpress with the blue line. There also seems to be a feature at 1350 or no 1380 that's completely missing or averaged out in the oreXpress spectra. So as you can see, there's information missing, and we see the same thing with the kaolinite spectra on the right. So there you can see there's significantly sharper features, a doublet in the middle at like 1410, things that have been averaged out by the higher or the lower resolution oreXpress. So when you have these features that are averaged, you start to get ambiguities between these different minerals, and that has implications for different applications. In this case, you may not be able to tell the difference between clay minerals if you're using an older spectrometer. Another great application is rare earth elements. They're often called the most critical metals to our modern world. They're essential in everything from renewable energy and electric vehicles to smartphones and advanced defense systems. Within this group of minerals, we have a subset called light rare earth elements, or LREEs. These are part of the lanthanide series, and they play a major role in modern technology. So rare earth elements often have these sharp features that distinguish them from one another. So the high resolution instruments perform significantly better for differentiating these rare earth elements. So as you can see here, you have the green line with the oreXpert data versus the oreXpress, and you can see a lot of features that are missing in the red line compared to the green line, which, like I said, can lead to misidentification of the mineral or ambiguities between a few different minerals. So now we'll be talking about applications with nickel. Nickel laterite ore deposits currently account for about 60% of the global nickel supply, and this percentage is only expected to increase. That makes laterites not just important today, but the dominant source of nickel in the future. So to maximize value from these deposits, we need precise mineral identification. A key challenge to distinguishing iron serpentine and magnesium serpentine, while they look similar in a hand sample, their chemistry and spectral features differ in very subtle but critical ways. This distinction matters because iron serpentine is concentrated during surface weathering reactions, making it an excellent proxy for nickel enrichment. And so being able to differentiate these two alterations is critical for identifying the efficacy of a mining operation. So on the right here, we have an example of spectra where we have a feature in, or a very subtle feature that's differentiating these two kinds of minerals. So that's something that's very important for nickel applications. And then we have talc. Talc has long been studied in its geological context, not just as an industrial mineral, but also because talc deposits can be associated with amphibole asbestos. That makes identifying and characterizing talc important for both economic and environmental reasons. When talc contains iron, we start to see a distinct ferrous iron feature around 1,000 nanometers. This is a subtle absorption band that can be tricky to resolve with standard resolution spectrometers because it often overlaps with other silicate features. With a high resolution instrument like the oreXpert, we can also detect an additional feature at 1400 nanometers where the OH bond interacts with Fe2 cation. These sharper, more diagnostic absorption features give us a much clearer fingerprint for talc, especially when it's iron bearing. So again, this is where high resolution really matters. It allows us to confidently identify talc and distinguish it for iron substitutions and better understand its geological and economical significance. And then we have alunite. What makes alunite especially useful is that its chemistry varies between potassium-rich and sodium-rich. By measuring the spectral shift between these two types, we can gain a clearer picture of the alteration environment. With high-resolution spectrometers, the subtle shifts in absorption bands are much easier to see, and that allows geologists to use alunite not only for identification, but also as a vector towards zones of higher potential of gold mineralization. So alunite is a perfect example of how resolution translates directly into exploration value. The better we can resolve those spectral shifts, the better we can target mineralization and continue to be profitable. Another critical resource is lithium. Lithium has become one of the most sought after elements in modern exploration, driven by demand for batteries and renewable energy technologies. One important lithium-bearing mineral is lepidolite, which can occur in mineable quantities. We often see lithium sourced both from brines, from hard rock pegmatites, with lepidolite being especially significant in the pegmatite setting. That makes being able to identify it quickly and accurately in the field very important. The challenge, however, is that lepidolite is spectrally very similar to muscovite, another mica that does not carry lithium. With a standard resolution spectrometer, the absorption feature of these two minerals can overlap, making them very difficult to tell apart. As you can see in this figure, we can see that there is a better definition on the feature with the oreXpert versus the standard resolution. So that gets us closer to differentiating these two minerals. Now, when using reflectance spectra, oftentimes the end goal is to quantify a different variable. So this could be in soil, quantifying different soil health metrics. This could be how much of this mineral is there versus another. And so oftentimes what is used is a partial least square regression. And where I'm going with this is that when you build a partial least square regression using higher resolution data, aka closer to the real reflectance or the real response of that rock, you're going to have a higher performance model, so long as the model is built with high resolution and the samples are collected with high resolution. So you can have higher performing or build higher performing models with higher resolution versus if you built a model with a coarser resolution instrument. And so here you can see an extra piece of features that is in our software, which is our model, chemometric modeling that's integrated into our software. So here you can port your model into our software, and every time a spectra is loaded or collected off of an outcrop or a soil sample or whatever, when you're in the field, you'll get a real-time estimate and prediction. And so here you can see our XRD prediction was 81.7, and this model that we had built is performing and predicting it at 86.6%. And so the performance of these models is entirely dependent on how much training data is in it, but you can get high quality data in the field and high quality response and accuracy without ever needing to do any real analysis. So that's all automated. And so some of the key conclusions here are that the oreXpert shows additional features or more defined features for a lot of different minerals that are important in industry. It's a great tool for alteration mapping and distinguishing between species of minerals. The future of field spectroscopy is in higher resolution. We're always marching towards better, higher resolution and better performing spectrometers. And since we've made such big advancements in recent years, there's a need for higher resolution mineral libraries, and we hope to see more of that in the future. So I'm going to thank you very much for attending our webinar, and I'm going to open it up to questions. So thank you.